Hey everyone, and welcome to today's Explainer. We're going to dive right into the fascinating, and let's be honest, kind of destructive world of mechanical testing. We are looking at the exact science of pushing materials to their absolute physical limits, literally pulling and stretching them until they snap, just so we can figure out exactly how they tick. I mean, if you've ever wondered how engineers can be so certain that a massive steel beam will actually hold up a skyscraper, or that an airplane wing isn't going to snap in turbulence, well, this right here is where that certainty begins.
So, here's our roadmap for today. We'll be covering why we break things, the tensile test explained, mapping the breaking point, true versus engineering stress, and finally, the anatomy of a fracture.
All right, part one, why we break things, pushing materials to the limit.
So think about this for a second. Why on earth do engineers take perfectly pristine metal components, lock them up in a laboratory, and intentionally destroy them? It seems completely counterintuitive, right? It's this inherent conflict between designing something to last forever and actually having to manufacture it into shape. But here's the thing, to truly understand what a material is capable of, we absolutely have to find out where it fails. We run these destructive tests where the specimen is basically ruined just to secure the hard data that keeps our built world standing.
You see, there's actually a massive philosophical split in engineering. On one hand, you have design engineers. They care about elastic properties. They want materials to act like a giant rubber band, resisting permanent deformation so that structures hold their shape no matter what stress they're under. But on the flip side, we have manufacturing engineers. Their whole goal is to push past those limits, to exceed the material's yield strength. They actually need the material to act more like modeling clay, focusing on its plastic properties so they can permanently mold and bend that metal into the specific shapes we need, like car panels or bolts.
So look, we're not just breaking things for the fun of it. Though, let's be real, it is pretty fun. We do it to unlock fundamental mechanical properties, to double-check the chemical recipes of the metals, to confirm they'll actually work in real-world applications, and, maybe most importantly, to expose any hidden defects in the raw materials before they ever make it into consumer hands. Moving right along to part two, the tensile test explained. Or, as I like to think of it, ripping metal apart.
Meet the undisputed heavyweight champion of our story, the tensile testing machine. What we do here is take a carefully prepared specimen, usually a standard ASTM round bar or maybe a sheet specimen marked with a standard 2-inch gauge length. We clamp it down firmly at both ends, and then we apply a highly controlled axial force. We literally just pull it apart. As the crosshead of the machine pulls down, it's constantly measuring two things: the exact load being applied and exactly how much the specimen is stretching or elongating.
Okay, let's walk through the exact life cycle of a metal specimen while it's trapped inside this machine. It all goes down in 6 distinct stages. Step 1 is just the baseline, original shape, zero load. Then, in step 2, the tension kicks in and the specimen starts undergoing what we call uniform elongation. By the time we hit step 3, we're at the absolute maximum load, which is also known as the ultimate tensile strength. After that, step 4 is where things get really critical. We see the onset of something called necking, which is basically plastic instability. Step 5 is the grand finale. The specimen completely fractures and snaps. And finally, step 6 just leaves us with the final broken pieces to measure.
Now check out how the physical cross-sectional area of the metal actively shrinks as it gets stretched. Especially in step 4, notice that harsh pinch right in the middle of the rod? That is the necking phase. The uniform stretching completely stops, and all that intense deformation becomes hyper-localized in that one specific spot, right before it totally fails in step 5. It is a highly visceral, physical transformation.
Part 3. Mapping the breaking point, decoding the data.
As dramatic as watching that physical break is, the real treasure here is the secret language of the data being spit out in real time by the machine's load cells and extensometers. Enter the engineering stress-strain curve. If you look at the graph, the vertical axis is tracking the load we're applying, and the horizontal axis is tracking the elongation. Notice how there are two very distinct territories here? First, you have that steep, straight line on the left. That's the elastic region. If you back off the load while you're in this zone, the metal just snaps right back to its original shape. But once that curve flattens out into that massive arch, we've officially entered the plastic region. In this zone, the deformation is 100% permanent.
Right there, exactly on the border between those two regions, is a crucial metric called yield strength, labeled Y on the curve. This is the point of no return. It marks the exact millisecond the material stops acting elastically and starts undergoing permanent plastic deformation. For our design engineers making buildings, this is the absolute maximum limit. But for our manufacturing engineers making parts, this is literally just the starting line.
Now, once we're hanging out in that plastic region, we start caring a whole lot about ductility. Ductility is basically how much permanent deformation, or strain, a material can take before it just gives up and fails. We measure this by looking at how much the specimen elongated or how much its cross-sectional area reduced before it finally fractured. So if you're a manufacturer trying to form metal into a really complex shape, increasing the material's ductility directly increases its formability. It tells you definitively how far you can stretch the stuff before it rips.
Okay, part 4. True versus engineering stress. Shortcut versus reality. So when we're calculating stress, which, just as a quick reminder, is force divided by area, we actually have a choice to make. Engineering stress is kind of a mathematical shortcut. It calculates the stress using the original, thicker starting area of the metal specimen. But hey, remember that necking phase we talked about? The metal's physically getting thinner as it stretches. True stress acknowledges that harsh reality. It calculates the stress using the instantaneous, actively thinning, actual area of the specimen at any given microsecond of the test. And because that actual area is constantly shrinking, true stress will always calculate higher than engineering stress in the plastic region. Just let that sink in for a second. How we choose to calculate that area completely changes our understanding of the material's true limits.
And this leads us to one of the most amazing plot twists in material physics. Because true stress accounts for that shrinking area, the true stress strain curve doesn't actually dip down before breaking like the engineering curve does. It rises continuously. This proves that the true stress required to keep deforming the metal actually increases as the strain increases. Put simply, as the metal stretches and deforms, it actually gets stronger. This mind-blowing phenomenon is called strain hardening.
Which brings us to part 5. Anatomy of a fracture, the dramatic finale.
Because as it turns out, not all breaks are created equal. Take a look at a highly ductile aluminum specimen. It fails with what we call a cup-cone fracture. You can clearly see the plastic region and all the remnants of microvoid formation. It stretched, it necked, and it gave us plenty of warning signs before it finally failed. But compare that to a brittle fracture, like you'd see in mild steel. The break there is totally flat, crystalline, and incredibly sudden. There's almost zero visible plastic deformation. It just snaps with absolutely no warning whatsoever.
So what's the ultimate takeaway from this explainer? Well, we've seen how pushing materials past their yield strength, tracking those intense stress-strain curves, and analyzing their fractures in a lab gives us these profound insights into how our world is built. The next time you're driving across a massive suspension bridge, or maybe hitting some turbulence in a commercial plane, I want you to ask yourself, what kind of fracture were these materials explicitly designed to avoid? Thanks to the destructive science of mechanical testing, engineers already know the answer. They broke it in the lab, so it won't break in the real world. Thanks for hanging out and learning with me today, and keep exploring.